We will begin very shortly, maybe in another 2 minutes.
Hello, can you hear?
Yes, yeah, we can hear you.
Sorry, everyone, I got a bit late. Yeah.
No problem, yeah, no problem.
No, I was planning to do it from my office, but then I realized I don't have enough charge, so I decided.
Okay.
Okay, so let me just open the. Can you see this? Oh, sorry, I have not yet shared it. Okay. Can you see the OneNote?
Yes, now we can see it.
Okay. Okay, fine. So yeah, so should I start?
Yes, I think you can start. Yeah.
Okay. Yeah, so thing is, Divakaran could not come today, probably. So Shobhan already explained to you. So I thought I'll just do something. So instead of, I don't know his plans, and rather than try to guess what he's going to do, if we can do next, maybe he will come next week. We'll see. But I thought I'll give a lecture which is kind of disjoint from it. Something of the kind that we don't do here, but maybe slightly something entertaining, possibly. Or maybe it's not, see, in analysis, one of the things about analysis is that in basic analysis, what we do, it's a little boring. That's the problem. Meaning that what you do is a lot of systematic stuff. You define some things and do things about the things you have defined. Sometimes these are important things that you define, so the whole thing is actually meaningful, but sometimes it's good to see, like I did in my first linear algebra class, to see things which have some concrete meaning, which you accept as natural outside of the defined terms, and see how some of the concepts arise naturally. Anyway, so what I thought I will talk about is this stuff about approximation by polynomials. It's going to be disjoint from everything else, all the other lectures. So you can just relax and listen, or you need not listen, whatever you wish. Okay. So many of you will probably know the following thing called the Weierstrass approximation theorem. Okay, so Weierstrass spelling is always a bit confusing. Okay, this is definitely not the. I think there is no E here. Okay, Strass approximation.
No, sir, it's correct, sir.
It's correct?
Yes.
Okay, thanks. Okay, what is Weierstrass approximation theorem? Have you seen this theorem? And what does anyone know?
Any continuous function can be uniformly approximated by sequence of polynomials.
Okay, it's almost correct, except you didn't say where and what are these
On a,
functions.
on a closed and bounded interval.
Okay, so the way you said it, a continuous function. Let me write exactly the sentence that you said. A continuous function on a closed bounded interval can be uniformly approximated by polynomials. Okay, so let's try to write it in other ways. Okay, so with some symbols maybe. Okay, so what does that mean? So any continuous function on a closed bounded interval. So let's take the interval to be AB. Okay, so if the interval is AB and f is a function from I to R, and the only assumption is continuous. Okay, that covers part of it. Continuous function on a closed bounded interval. Then there are some other terms, polynomials, and something about uniformly approximated. Now, polynomials we know. Polynomials are functions of the form a0 plus a1x plus a2x square plus anx to the n, right? So those are polynomials. So what is uniformly approximated mean? What does it mean? Yes, anyone? What does uniformly approximated by polynomials mean? Yeah. So this is half of the first half of the sentence.
The approximation depends only on the epsilon or not on the x.
No, but what is it? What does it mean? Uniformly approximated by polynomials. What do I write here? A mathematical statement. What is the statement I should write?
So given epsilon,
Modulus of
epsilon
Pn
minus
modulus of Pn minus f is less than epsilon for a given epsilon.
Okay, first, what do I fix first? I fix Pn or
Epsilon.
okay, so then let's say given epsilon positive, what is the statement?
there exists a polynomial
There exists a polynomial
px
which we'll call px. So just to say again, polynomial means it will look like this. Such that
modulus of fx minus px
fx minus px
is less than epsilon for all x in AB.
For all x in the interval I, right? So this is one statement one. The same thing written in symbols here. Okay. So there are other ways to write it. So another way to write it is, what other way? I mean, somebody said Pn. So there was a sequence of polynomials. Can you write it in terms of sequence of polynomials? I just want to, I mean, this is more of what you were doing. So just to be able to rephrase the same thing in different ways. Can you say this in terms of sequences, this statement?
Yes, sir. For this epsilon, we will get some n. And that will be independent of x. So that modulus of Pn x minus fx is less than epsilon.
Yeah, but that is still, that is just, you're just calling P as Pn. That's all, right?
There exists a sequence Pn of polynomials.
Okay, so let me take this same statement again. Again, I have from I to R continuous, that is fixed. I is again AB.
Yes.
Okay, so then you're saying there exists.
Given epsilon. Yeah.
Do you fix epsilon? What do you want to say?
Given epsilon positive, there exists a sequence Pn.
Such that?
There exists a threshold integer k such that for all x in AB, Pnx minus fx will be smaller than epsilon for all x and all n greater than or equal to k.
Yeah, but that is here it is said 1, and you are saying that you can find a sequence. I can take this P and put it infinitely many times, right? So you understand what I mean? I mean, so what does it have to do with epsilon? So you are saying given epsilon, there is a sequence of polynomials satisfying this for all large n.
Yes.
No, but that is not what I want. But that is same as this statement. I can take this polynomial and put it infinitely many times.
Okay.
Just a second, I'll plug in my laptop. Yeah, go ahead. So something else about a sequence.
Is it that there exists a sequence of polynomials which converges uniformly?
Right.
I mean,
Okay.
that means, yeah.
Yes. So this is the way you want to phrase it. So no epsilon. Without epsilon, you would say that there exists a sequence of polynomials Pn such that Pn converges to F uniformly on I. Okay, that is another way to say it. What is converging uniformly meaning?
Now it's basically which the other participant said. I mean, for a epsilon, you could, I mean, for a given epsilon, after some stage of n, the Pn is close enough to F.
This is one
So
way of
for
saying it. That is one way of saying it. Let me just say the same thing in many ways. So this is just to see that how many different ways you can say the same statement. Okay, so here let me say it in another way. So
Yeah, norm will be less than epsilon.
Okay, so the same. Okay, so let's put it like that. So all this part is the same. So there is a sequence of polynomials Pn such that F minus Pn, somebody said norm, converges to 0 as n goes to infinity. What is this norm?
Supremum, sup norm.
Okay, where norm of a function g is defined as the
supremum of gx over
not
AB.
gx, absolute value of gx over all x in I. For any continuous function, continuous. Why do I assume continuous? I mean, just for
in that
definition.
case, supreme will be guaranteed to exist.
Supremum will be finite and it will be in fact attained. That is one of, you have not, I know that Divakaran had not yet gotten to all the things about continuity, but you know these things, that a continuous function on a closed bounded interval in fact attains its maximum and minimum. In particular, it's bounded definitely. So the supremum is finite. So what we are saying is that this norm is just the supremum of f of x minus Pn of x over all x. So that it goes to 0. Okay. So is there any other way to state it? Just changing it slightly. Let me state it one more way, the same thing. Okay. So consider C01. What is C01? Have you seen this object?
All continuous function from 0 to 1.
It is the set of all continuous functions from, I could have written C of I instead of, why did I change to 01? Let me write C of I. Sorry. So for that C of I is the set of all f from I to R such that f is continuous on I. Okay. Now P let's say, is the set of all polynomials. This we saw in the linear algebra class, right? So set of all polynomials with real coefficients. The degree is not fixed, n is greater than or equal to 0 and aj in real. So this is the set of all polynomials. So how can I phrase it in terms of these two sets? C of I, by the way, is a metric space. So this is a metric space with what is the distance function there? How do you measure the distance of two things?
With that norm.
Using the norm. Okay, so let me write it properly. So the distance between two functions is defined as supremum of that same f minus g, which I have defined above. That is sup over x in I, f of x minus g of x. This is actually a metric space. This is something you have to check. You probably know this, that this C of I becomes a metric space with this metric. Now, what is the statement of Weierstrass in terms of this C of I and this P?
This case it's all the points are limit points.
So
All the points of CI are limit points of the space.
Does that have is there a name for that?
Yeah, dense. It is dense.
P is dense in C of I. Yeah.
Then P is dense in C of I. Okay, so this set is dense in that metric space. See, there are so many different ways of saying the same thing. There is slight change of perspective. Okay, so what is the change of perspective? It is a very important change of perspective, which is now we take for granted, but that was something a little big when it happened. When Weierstrass first stated it, probably he did it like this. So if you have a function, then you can find a polynomial and give epsilon, then you can, this and this are all very close. Okay, finding a sequence close to going to that and finding for every epsilon a p such that this happens. It's the same thing. But when we come to this, we are actually talking in the language of functional analysis. So functional analysis, what is functional analysis? It is this idea that we think of a space of functions where every point is a function. Function itself, when you first see function is it's a mapping from one set to another and so on. But this perspective where we think of each function from I to R as a point of some space, that is the functional analytic viewpoint. Here we are not fixing an F or any such thing. What we are saying is we look at this space and this P is dense in that C of I. Okay, so that is the statement. So, but all these are the same. You can see the equivalence of these things. Okay, so that is just to get some perspective on, terms that you have already learned. I just restated in different ways. But however many times we restate, we haven't actually proved it. Is it something that you teach the proof of in your courses? Do you teach proof of this?
No.
This is not there in syllabus. Is there anybody who has taught this in class as proof? With proof? See, sometimes it is necessary to tell. Even if you don't have, I cannot tell you how to teach. As I said on the first day, I don't really know. But sometimes I have found that in mathematics, even if you cannot prove it, it's sometimes useful to spend time just telling interesting things. So even if you don't have time to prove, you can tell something interesting. Now, why is that? What is the point? In mathematics classes tend to be a little too serious, okay, for my taste. You start with definition, then proof, theorem, proof, like this. But it is, as somebody once told me, what we do in mathematics class is a bit like you go to a language class, say English or whatever, Kannada, whatever your language is. And then you study a whole semester, you are studying the alphabet and how to write the alphabet and so on. But to really get somebody interested, you should tell them something interesting. Maybe read a poem or read a story, tell a story in that language, etc. But so the analogous thing should be done in mathematics. Even if you cannot prove a theorem, sometimes you should tell some interesting facts which people will appreciate. The main thing is to get interested. Once people get interested, they can do a lot of things on their own or with all the resources of the internet. But getting interested is the key point. And so from that point of view, I would strongly encourage this as a nice theorem, which all the terms are already there. You can tell them, even if you don't prove them. Now, does anyone know how to prove this theorem? Has anybody seen a proof of this theorem? No one?
There is one way we can prove with the help of Bernstein polynomials.
Okay. So Bernstein polynomial. Okay. So there is a way, there is a very, very beautiful proof. It's exactly what you said. The motivation for it comes from probability, but you don't need to know probability. I'll tell you what the motivation of probability is. But so let me recap the proof of this. So the proof of Weierstrass approximation theorem. So there are multiple proofs. Okay, there are multiple proofs. A natural one, which I will not go into, is the following. What is a natural generalization of polynomials? When you look at polynomials, you see some expression like this, right? So think of your real analysis class. What is something that looks like this, more general?
Power series.
Power series.
Very good. So power series. What do you call a function which can be, which has, do all functions have power series? If I give you a function, can you write a power series for that?
No.
So when can't you write? I mean, what is an example? Why can't you write?
If the function is differentiable, we can use the Maclaurin series.
How many times it has to be differentiable?
It has to be differentiable. Infinitely differentiable.
It has to be infinitely. So first, I am talking about a slight distraction here. So suppose I have a function from some I to R. So let's take I to be 0, 1, first of all. So can we expand F in power series? This is itself a very interesting question of analysis. So that is, you want to, what does it mean to say expand in power series? You want to write it as sum of with some coefficients.
X raised to
X minus X
n.
naught something.
X minus X naught raised to the power n for some X naught, which should be in the interval, and for all X in the interval, and for some ANs. ANs are some real numbers. Okay. So is it possible? So can you tell me what is a necessary condition? I mean, what is needed? You already told me this, so I'm just asking to repeat.
Analytic function should be analytic.
But that's a name. So, but before that, you said something which
Infinitely differentiable.
So it has to be differentiable infinitely many times. Okay. So the answer is no. Okay. So F has to be differentiable infinitely many times. Yeah, is that enough? If F is differentiable is infinitely many times, will it have a power series? So easily we can make up functions which are not differentiable, right? So if I take 0, 1 and I take something like this, this is the function mod x minus half. That looks like this, right? So it is not differentiable. Even if I assume continuous, it is not differentiable. So this cannot be expanded in power series because it's not differentiable. Okay, power series will be differentiable. So what is that enough?
It should be differentiable around a particular point.
Right, it should, let's say it's differentiable everywhere.
Continuously differentiable, I think.
Well, what does that mean?
No, it is not sufficient.
What is continuously differentiable? Continuously differentiable means differentiable once and the derivative is continuous. Here I have assumed much more. Yes, once you can differentiate, but what you get is not only continuous, you can differentiate again. And what you get is not only continuous, you can differentiate again. I have assumed you can differentiate infinitely many times. So continuously differentiable is already included here, meaning this includes continuous differentiability. Let's put it that way, right? So, but is that sufficient? If a function has infinitely many derivatives, if you can differentiate forever, then can you write it as a power series?
No.
No. Okay. Do you know why not? Is there any example of a function which is infinitely differentiable, which you cannot write as a power series? This is a very famous function. You may or may not do this actually. But
e to the power minus 1 by x square, no?
Right. Okay. So the function which you may have seen, if you may have seen and not appreciated why they brought this function up. So this is a very strange function.
Becomes a plateau.
Yeah, but what is
zero.
the function you want? E to the minus 1 by
x square.
And for what x?
X not equal to 0 and 0 for x equal to 0.
So what it does is it looks like this, e to the minus 1 by x square, right? 1 by x square is decreasing, minus 1 by x square will be increasing, e to the minus that. So at x equal to 0, it is minus infinity, e to the minus infinity is 0. Okay, e to the minus infinity is 0. And then what happens if you increase x? This is a large number, so it will look like this. You don't see much difference between this and a parabola. That's what it may look like. Okay, so this is 0 and it looks like this. It will have 0 derivative, etc. So this function, it turns out, it looks like a parabola. It's not parabola, it's very different. And why this e to the minus 1 by x square? Why do you need to put something like that to make it not a power series? So what you know is that here, what is the funny property of this function?
It has all the derivatives 0 at 0.
So it turns out all derivatives near 0 are 0. Okay, this is something, if you really understand analysis, this is a good test. Can you see that this is actually 0, all the derivatives, without doing calculation? Okay, without doing calculation, can we see this? This is a kind of thing which we have not actually spent time on here, but it is an important thing. So what is analysis? Analysis is a lot about growth and decay of functions. Okay, so to know what is large, what is small, etc. So what does derivative mean? I mean, so when you talk about a function which has some derivative, suppose, let's say at 0. So what is the derivative at 0? It is the limit as x goes to 0 of f of x divided by x. That means if suppose the derivative is not 0, what does it mean? It means near that it looks like a line. Okay, not sleeping line, but a line. So it will be like this. So there will be a tangent line which is not sleeping. Now it's not horizontal. Okay. So what does f dash of 0 equal to 0, f double dash of 0 not equal to 0 mean? Then what will the function look like? So this function, this means f looks like a line. What does this mean? F looks like? What does f look like if this is the case? So can you give me a function for which derivative is 0 but second derivative is not 0?
X cubed.
Not x cubed, x squared. I want second derivative not 0, right?
No, okay, sorry. Yes.
X squared. So this looks like x squared. So it will look like this. So it approaches 0 much faster. Okay, when you go to x, when x goes to 0, it goes to, this one was going to 0 at the rate of x. If x goes to 0, let's say f of 0 is 0. That's what I'm implying here. So fx goes to 0 at the rate of x. Here fx goes to 0 at the rate of x squared. And so on like that. If the first 10 derivatives are 0 and the 11th derivative is not 0, that means as x approaches 0, fx approaches 0 at the rate of x to the power 10. That is how you think of it. So it vanishes faster and faster. If many derivatives are 0, it means the vanishing is faster, which means the growth is slower. So now when you look at something like e to the minus 1 over x squared, that goes to, the thing is, exponential function goes faster than any power. Here everything is inverted, and this one, it decays faster than any power. So that is the reason. Zero, as x goes to 0, faster than any power of x. It goes to 0 faster than any power of x. So it will go to 0 faster than x power 10, which will show that the first 10 derivatives are 0. It will go to 0 faster than the first 100 powers of 10. So all the first 100 derivatives are 0. Every derivative is 0. That's what it is. Okay, this was a digression, but it's an interesting digression into something that you have perhaps seen. And you probably proved this by calculation, but I emphasize it again. You should train yourself to see this, that if f is e to the minus 1 by x squared, then all the derivatives are in fact 0. That is something that you have to intuitively get used to. Or you have to develop your intuition to the point that this becomes clear. So once that happens, it turns out that you cannot expand it in power series. Okay, so this was a digression I went into, but why did I go into that digression at all? If I lost you in all this, don't worry about it. Let's come back to Weierstrass theorem. The question was approximating f by polynomials. So why did I go into this power series business? One approach to Weierstrass approximation theorem is this. Okay, so let's generalize polynomials to power series functions. First, if you can approximate a continuous function by a power series, then can you approximate a power series by a polynomial? Let's put it this way. Suppose I have a power series. Can I approximate it by a polynomial?
You can do.
You just cut the number of terms at some large n. Okay, that's how you approximate a power series by a polynomial. If you cut at 1 million terms, you get a polynomial, right? This will become a polynomial. So if you cut this series to any number of terms, you get a polynomial. By cutting it at a very large number, you can approximate any power series by a polynomial. And in fact, we can do it uniformly, etc. That is part of what you learn in power series about uniform convergence of series and all that. You do that. So I'm just dropping those words. I'm not talking about it there. But if it was true that all continuous functions had power series, we would be done, because power series, it is kind of clear that we can approximate by polynomials. But it's not true that continuous functions have power series. So there is a second step where you have to show that a continuous function can be approximated uniformly by a power series. So Weierstrass' original proof was like that. He broke it into two stages. First, where he approximated the continuous function by a power series, and then the power series by a polynomial. Okay. So let's not do that. So this all is a digression. So as I said, if I lost you, forget it. All this is not needed. I will give a separate proof along the lines that you already suggested, namely Bernstein polynomials. So all this digression you can forget. Let's come back here. So let f be a continuous function. So let's do it on 0, 1 to r. It's enough to do it on 0, 1 to R for a reason that is not too difficult. You can scale, you can transform 0, 1 to AB by a linear transformation, meaning you send x to ax plus b minus a or something like that. You get that. Okay, so anyway, it's enough to do it on 0, 1. Let's do it on 0, 1. Okay, be continuous. So Bernstein came up with a very magical proof. I mean, it was an amazing proof. Bernstein defined the following polynomial. Said, let Pn of x. So if you want to write a polynomial, it is natural to, okay, you tell me what coefficients to put. But he wrote it in a very strange way. He wrote this function, n choose k, f of k divided by n. F is the function you are starting with. The sum goes from k equals 0 to n, and x to the k times 1 minus x to the power n minus k. Okay. So this is actually a polynomial. It's not written in the standard way that polynomials are written, where you write it in terms of powers of x. Here, x to the k is there, but also a 1 minus x to the n minus k is there. But no problem. If you expand everything and do it, you will get a polynomial. That is clear, right? But the coefficients will be very complicated. Don't bother to do that. If you try to expand it and write it, it will get too complicated. Let's not do that. But this is a polynomial. P is a polynomial. What is its degree? Not that I need, but just a curiosity question. What is the degree of this? See, the point is all these are coefficients, okay? X is only here. So what is the maximum power of x that can come?
N.
Yeah. So of n. It's actually of degree n. But okay, as of now, I can only know it's less than equal to n. But because when I expand everything, maybe that will cancel. Who knows? So degree, in fact, equal to n. But let's write a less than equal to n. That's what we can see. Now, why is this? So the claim is that Pn minus f, the sup norm, goes to 0 as n goes to infinity. Then you are done, right? This would prove Weierstrass because you have produced polynomials which converge to f. Okay, so you have produced polynomials. Any questions about this? I mean, is it clear what is going on? It's a very strange thing. He wrote down an answer. Okay, so these are coefficients. Means not coefficients of x power k, but coefficients of some. He's taking a, so these are not depending on x. That's what I mean. They don't depend on x. This part depends on x. And this is a polynomial. And claim is that this polynomial goes close to f. Why is that so? Yeah. Anyone? Yes. I mean, have you seen it? Okay, it's not easy at all. This is not easy at all. But am I making sense? Shall I proceed with proving this?
Yes, sir.
It is more involved than any other things we have done in the course. At least I have done in the course. But it may be something interesting to see. Okay, it may be more difficult than the things you have seen, but it is typically how things are done in analysis. Okay, it's a great lesson in analysis, this proof. So to prove, we make some observations. So I will write the first observation is that what happens when I sum k equals 0 to n, n choose k, x to the power k, 1 minus x to the power of n minus k. What do I get? What is this?
This is 1.
Binomial expansion.
1.
Exactly, binomial expansion. This is the expansion of x plus 1 minus x whole raised to the power n. If you expand that in binomial series, you will get n choose k, x power k, 1 minus x power n minus k. But this is just 1, right? X plus 1 minus x is 1, power n is 1. Okay, so this is 1. This is the first observation. So this is what in probability you see as a binomial distribution. Okay. Second point to note. Okay, so this is first let me write it pictorially and then write the exact thing. Okay, this is the key. This will be key to the whole thing. So what if I plot this? Actually, I can plot it. Hold on. Why should I say if I plot it? I can actually plot it. Let me open. Okay, let me open. Okay, I could open Mathematica, but let me just open Wolfram Alpha. It's okay. I will share with you in a moment. Hopefully that will be sufficient to do. Okay, so let me actually let me share. Okay. Can you see this web browser where I have?
Yes, sir.
Okay.
Yes, sir.
So let us do. So let's take some n. Okay. So let's take some n, which I will take to be, let's say 20. Okay. So I am going to do binomial n comma k, and then x I have to take to be something. First, let us take x to be 0.1/4. Okay, 1/4 to the power k. And what is 1 minus x then? 1 minus x will be 3/4 to the power of 20 minus k, right? Do you understand actually? Do you see this? I mean, is it legible? I mean, is it readable what you see here?
Yes.
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 This binomial 20 comma k is the way it is written in this language of 20 choose k. This is 20 choose k. Then I have taken x to be 1/4 and 1 minus x will be 3/4, and you plot this. So I plot this from what is the k from 0 to 20. K goes from 0 to 20, right? Binomial coefficient. So let's plot this and see what we get. So it is doing, hopefully it will give. Yeah, interpreting. What happened to it? It's being very slow. Maybe I should have opened the Mathematica, but that also takes time. Okay. Where is the list plot? Oh, this is binomial. I don't understand what is its problem.
Can we use just plot?
No, it is a list plot. In Mathematica, plot is for functions. But why is it interpreting binomial? I mean, I don't know. It's in. No, it is binomial. Okay, it's very strange. I don't know why it is not understanding what I'm saying.
Does alpha take Wolfram commands? I thought
Yeah,
they also use it.
I have done it many times actually. I mean, even this. Okay, it's a bit strange that it is not doing. So what else can I do? I mean, okay, so maybe I should stop share of this. Sorry, I mean, I will, okay. So sorry about that. I mean, it is something that I could have shown, but it's for some reason it's not showing it that way. But let's do it since I have about 15 minutes. Let me just tell you what happens. We can in fact prove it also. So what happens when you plot? So here I'm going to plot k this way, and I'm going to plot n choose k.
Sorry, you haven't shared your screen.
Oh, I have to share again. Oh, sorry. Yeah. Where did the Zoom go? Okay, I must share again. Okay. Is it visible?
Yes, sir.
So let's plot here. K goes from 0, 1, 2 up to n. So what do these numbers look like? If I plot, when k is 0, it will give me x to the n choose 0 is 1, x to the power n, and 1 minus x to the power 0. So x to the power n. Okay, it will be some number here. So do you know what this looks like, binomial distribution?
Looks like the normal curve.
Right. It goes up to a point and then it starts coming down. In the end, it will be 1 minus x to the power n. What is the place where it goes to the maximum? Do you know that?
NP.
It's the mean.
This will be n times x. Okay, very good. So that is where, so you can, how you do that? How can you say it goes up and comes down? You take successive ratios of these and then you will see that it goes up and comes down. The main point of this, what I wanted to say here is that that point is not required, but what I want to say here is that these numbers, they add up to 1, right? We can think of it like probability numbers. I mean, they add up to 1, but the maximum is at nx. So the thing is, so let me write in words and then explain what it is saying. Most of the mass of binomial distribution is in a square root n neighborhood of nx. Okay. In other words, I'll write in words. This is an informal statement. What it means is the following. If I look at the same sum, n choose k, x to the power k, 1 minus x to the power n minus k. But now I do k goes from 0 to n, but I do not do all k. I take only those k which are not close to nx. So that is k minus n minus So if I write if I write k by n minus x, suppose I write greater than equal to delta. So I'm summing only over those k which are not close to nx. Okay, so that means I take, so this means I take nx minus, so n times x minus delta, n times x plus delta. So these ones are not taken. So only the coefficients up to n times x minus delta and after n times x plus delta, they are taken. Okay, that's what it means. So this, the claim is that, so this is a partial sum. So now you can't use binomial formula. What is this sum going to be like? The statement is that all the really, this whole 1, this total is 1, right? The claim is that all that 1 is coming close to nx. That means if I omit all the k which is not close to nx, I get something very small. And the answer is that this is smaller than, let me think for a moment. It is smaller than, I'll tell you what it is, nx 1 minus x over n squared delta squared. Okay, so this is what you get. So the n cancels. So I have not proved this. Maybe at the end I will tell how this is. Let us see how to prove. So which anyway, x into 1 minus x, by the way, is smaller than 1, right? It is smaller than 1. Because x and 1 minus x are, so this is important. So it is smaller than 1 because x into, this is true for any delta. So I will maybe not prove this, but since let me tell here, this is one of the most important facts that any mathematically literate person should know. This is nothing to do with Weierstrass and other things. Okay, maybe I'll come back to that after I prove Weierstrass. I'll tell you what this thing is saying. But this is a very important fact. Let's assume this. If we assume this, what is happening? Okay. So the way to think of it is like this. We are multiplying f of k by n by this n choose k x to the k 1 minus x to the n minus k. Okay, let's assume the extreme situation here. Suppose the sum is 1 and only this one is 1 and all the others are 0. One way the sum could be 1 is that this coefficient at x is 1 and all the others are 0. Suppose that's not true, but suppose that was true. Okay, then what would we get here? What would this polynomial be? Suppose n choose k x power k 1 minus x power n minus k was looking like this. It doesn't look like this, but imagine that it was 0, 0, 0 everywhere and only here it was 1. And everywhere it was 0, suppose. Suppose that was the case, then what happens here? Which term remains? See, if n choose k x power k 1 minus x power n minus k was 0 for all k except the k closest to nx.
Nx for k.
Only k close to nx will survive. All the other terms will be 0. So this will be like only one term.
Okay.
K equal to nx, and there n choose k, this thing will be 1. So what will you get? F of k by n will be x.
F of x. Yeah.
F of x. That is the idea. So if these coefficients were 0 here, 1 here, 0 here, it would just get fx. Or strictly speaking, you don't get fx, you will get f of k by n, where k is the closest integer to nx, but that will be very close to x. Okay, k by n will be very close to x. So that will be like fx. But here, that's something like that is happening. It's not exactly 0 and 1. So we have to analyze that. So let's analyze that. So now look at f of x minus p of x. Okay. So what is f of x minus p of x? F of x minus, I'm writing again because that is not visible now, is k equals 0 to n choose k, x power k, 1 minus x power n minus k times f of k over n. Okay, which you can still add up. I can write like this, because the sum of these numbers is 1, right? The sum of all those numbers is 1. I can write the first term as f of x times the sum of all this without the f of k by n. When I do that, what I get is, let me write it and then explain, x power k, 1 minus x to the power n minus k, f of x minus f of k by n. Okay? So let me put a bracket around that. Because the first term, fx will come out of the sum and this sum is 1. So that is fx. The second one is this px, what we have written. Okay? So this is what we get. Now the point is, so we are trying to bound f of x minus p of x uniformly, right? We want to get a bound on this uniformly over x. So how do I get a bound on this? Let's put the absolute values inside the sum. You use triangle inequality, put absolute values inside the sum. These are positive terms. I don't need to write absolute value. What I get is f of k by n minus f of x. Okay, I had written f of x minus f of, same thing. The absolute value of that. Okay, so this is what we get. Now, why is this small? That is the whole point. Why is this small? I already explained. But now let me explain the same thing in a different way. So this one, there are two possibilities. You divide this sum into two parts. Sum over all k, for which k by n minus x is less than equal to delta, and the sum over all k, for which k by n minus x is bigger than delta. Okay, let's take this sum. Same thing here and here. This is the standard way of proving things in analysis. You have to break into two things. There are many terms here. There are two types of terms. Those k for which k is close to n, k by n is close to x, and those terms for which, and this is small for one reason, this is small for a different reason. That's what we need to understand. Why is this small? Can you tell me why these terms are small in some sense?
F is continuous.
Because here k by n is close to x, so f of k by n is close to f of x. So this term is small. Okay. And what happens here? Here we don't know, k by n is away from x. F of k by n minus f of x need not be small. But what we know is that the sum of all these numbers is small. Okay, that's what we are going to do. Okay, so let me write here. Okay. Sorry, I will just turn off the phone. Okay, so I'll just do it quickly. Okay, so let us be here. So let's call this 1 and call this 2. So 1 and 2 are small for different reasons. The term 1, what we will do is k such that k by n minus x less than equal to delta. This thing, n choose k, x power k, 1 minus x to the n minus k times f of k by n minus f of x. Okay. This I can bound by what I will call omega f of delta. I will tell you what that is, times sum over k, n choose k, x power k, 1 minus x power n minus k. Now what is omega f of delta? This is the maximum of f of u minus f of v when u and v are within delta of each other. This is called modulus of continuity. What is the maximum difference in the values of f when u and v are within delta of each other? Okay, so that is what this number is. Because k by n and x are within delta of each other, right? You see k by n minus x is less than delta. So f of k by n minus f of x is smaller than this number, which is the maximum over all points, pairs of points, which are at distance delta or less. So this number will be smaller than this. And what is this sum? Okay, this is in fact over k by n minus x less than equal to delta. But even if I sum it over all k, what does this become?
1.
That is 1. So this is omega f of delta and this is 1. Okay. If I extend, so less than equal to 1. What about the second term? Second term is over k by n minus x bigger than delta. So second one, let me write. So it's 6:59. Maybe I take 2-3 minutes. Is that okay, so Shobhan?
It's 7 o'clock.
Yeah, sure. Yeah.
So it is k such that k by n minus x is bigger than delta of the same sort of things. N choose k, x power k, 1 minus x power n minus k, and f of k by n minus f of x. Now, this one is not small. How big is it? This is an annoying term. I would like to remove this. How bad can it be? How big can this be? This can be at most 2 times.
2 times norm of f.
Exactly. 2 times the norm of f. See, the maximum modulus of f is this norm f. So f of, you use triangle inequality. The difference is smaller than absolute value of f of k by n plus absolute value of f of x, which is at most 2 times the norm of f. And then what remains is the sum over k such that k over n minus x is larger than delta of n choose k, x power k, 1 minus x power n minus k, which we know, I already said that this sum is smaller than something. We will take that, smaller than 1 by n delta square. So you get that this is smaller than 2 norm f over n delta square. Okay. So you see the bounds we get don't depend on x. So what we have shown is what is it we did? We started with fx minus px, and the bound for fx minus px is 1 plus 2. It is smaller than this. So what we have shown is the subnorm between f minus pn is smaller than or equal to this number omega f of delta plus 2 times norm f divided by n delta square. Okay. Now, how can I make this small? So what happens as delta goes to 0 to this thing?
Goes to 0.
That is the uniform continuity. So given epsilon positive, there exists delta positive such that omega f of delta is smaller than epsilon. This is the uniform continuity of f. If it is not clear, you have to think why this is uniform continuity of f. Okay, think about it. So first I do that. So this becomes smaller than epsilon plus, now I have fixed the delta, 2 norm f over delta squared n. Now what do I do?
Increase n.
Pick n larger than, so pick n larger than, large, so that second term is smaller than epsilon. I can do that. I can let n go to infinity. This will go to 0. So this whole term will become smaller than 2 epsilon. So that's what we wanted to show. I can find a polynomial such that this is smaller than 2 epsilon. Okay, so it's already time. So I'll stop here. If there are any questions, you're welcome to ask. There were some other interesting things that I had thought I would say, but there is no time. So we'll stop here. Okay. Are there any questions?
Professor Nandakumaran is also here. Yeah. Good evening, sir. Yeah.
Good evening. Good evening.
Oh, hi, Manj.
Hi, Manju.
Okay, I'm almost done. I will leave to you. So it start at 7:10, right?
Yes. We take a small break of.
Right.
We will start at 7:10. Yeah. In between, if anyone has any questions, you can ask.
Yeah.
Sir, I have a doubt in one line.
Yes, please go ahead.
Yes. Yeah. Next.
Further down here.
No.
Here
or downside? More. Yeah. This one. This is 2 times norm f. Mod of f of k by n minus fx is less than equal to
this is
2 times.
Yes. This is bounded by, that is because this is just smaller than, this is this is smaller than or equal to f of k by n plus f of x. And both of them are smaller than norm f, right? Okay. Absolute value of f at any point is smaller than norm f. This is the sup norm.
Okay.
Is that okay?
Yes, sir.
Okay. Okay. So nobody has a question. Maybe I went too fast or it was not clear. But since nobody is even asking, let me myself tell that this thing I said is one of the most important points in basic probability. I have not shown this, but this is exactly the reason why all your opinion polls, everything works. What you do is you take a sample, so you want to know how many people will vote for party A and how many people will vote for party B. What do? You take a sample of voters, you ask, will you vote for party A? And you write down 1 if yes and 0 if no. And then you take that average and you say that, okay, if you get some 20% there, to say that, yeah, in the whole population, 20% of people are going to vote for this party A. The reason you can tell that is precisely this business. Okay, so this whole thing, what is written here, this is really a justification of using poles to do this. And the way to derive it is by what is called Chebyshev's inequality, which I have not talked about. Okay. But okay, I will leave it at that. I'll stop now. So Nandakumaran, you're doing from home or are you in campus?
Home. From home. Home.
Home. Okay.
Yeah. Yeah, I don't go to campus much. You are in the department now?
No. I had been there, but I taught my class. Then it turned out my computer had very low charge, so I came back to my home. I didn't have my result. Yeah. Now I'm at home.
Okay. So how is it? It's going on quite well for the last 2 weeks.
Really have to ask the participants. So Shobhan, you can answer.
Sure.
Yeah, I think, I mean, according to me, it's going well. I think participants would be much better to answer the question. Yeah, anyone wants to say something? How is it going?
Yeah, it's going on very well from Pradima.
Okay.
Actually, I want to say something actually to Professor Manjunath. I'm working in approximation theory, and I was seeing all these things. It's like though I have done some work in this in approximation theory, but for me it was very, very interesting. So I can totally relate to this lecture.
Okay, thank you. So yeah, if one person likes a lecture, it is a success for me. So
yeah.
Now compared to my usual success here. So but thanks. Yeah. Maybe Nandakumaran can share if he wants.
Yeah.
So Shobhan will say when to start.
Yeah, I think we will start in a minute. Yeah.
Yeah, sure. No problem. So shall I try sharing my screen?
Yes, you can try. Yeah.
It says that you cannot start share while the other participant is.
Yeah, I'll just stop sharing. Yes. Okay, I think it's time. Let me quickly introduce Professor Nandakumaran. So Professor Nandakumaran is currently working in Indian Institute of Sciences, Bangalore. His research interests are analysis and differential equations. He has published several research articles in reputed journals. He has co-authored 2 beautiful books in ordinary and partial differential equation. He has also been conducting online courses through NPTEL, which is freely available online and benefits several students and lecturers in the remotest place of India. He had held several positions and is member of several mathematical organizations like American Mathematical Society and National Academy of Sciences, India. He is also currently the convener of KVPY. So without further ado, I welcome Professor Nandakumaran to start his talk.
Okay, thank you, Shobhan, and also Manjunath for inviting me to this. I'm looking for my pen. Thank you. Yeah. So we are going to talk on multivariable calculus, and there are 8 to 9 lectures in this series, and is given by 2 of us. I'm audible, right?
Yes, sir.
Okay. And I'll be giving the first 4 to 5 lectures and on total derivatives, inverse and implicit function theorems. And I hope, I'm sure you would have heard about something. These things, something is okay. And so the main aim is to prove inverse function and implicit function theorem. Maybe I will explain a little bit about rank theorem. But in the second half, my colleague Purvi Gupta will be doing the thing. And let me settle. And she may do it probably divergence theorem, Gauss theorem, and all that. That's are all important fundamental theorems. And all these topics, for example, multivariable calculus is one of the most useful subject in analysis. And it's nearly impossible to do any worthwhile applications. It's not just in mathematics, and it's any other subjects, like whether it is engineering or any other topic, any science. If you don't know, most of the physical problems like minimization problems and other things, you need to understand multivariable. So we may not be going into details in the very infinite dimensional setup. Many of these theorems are naturally generalizable to infinite dimensions. And usefulness comes when it is more useful it is when it is you understand these concepts in infinite dimensional setup. Because if you want to look for solutions in the infinite dimensional spaces, physical solutions will be sitting in infinite dimensional space. So what I will be doing here is to mainly motivate this thing, not that we give all the proofs, but I will try to give nearly a complete proof of inverse function theorem and set the proof of implicit function theorem. And something related result is called a rank theorem. We will try to explain to you. So the main idea is to motivate you how all these derivatives can be defined. So excuse me if you are already an expert in all these things. So it's a very, very elementary level, which you should know it. If you are already know, it's well and good. It's not just learning definitions and proof of theorem, rather understand the theorem. Understanding theorem is not just read the theorem. So there are lot of references you can look into that, but I myself restricted to this Rudin principles, which is first one of the early book which you are all familiar. And then there are books on Tom Apostel calculus and also mathematical analysis. There are 2 volumes. So my reference would be 1, 2, and then 3. But if you want to understand these things, even finite dimension, but in a more general setting called manifolds and other things, you can look for what are these manifolds and other things. Then, of course, infinite dimension setup. Maybe my TAs, teaching assistants, may do work out a couple of problems from infinite dimension. If I get time, I will also try to do something, at least an example, because I think I got an extra hour. So possible I will do it. So let me start with something. So what we are going to do is solvability. Okay. Solvability. So solvability of equations. As I said, you will see I will start with examples. So just to start something, the solvability can be from some space to another space. You have to later think. So there are 2 ways of doing. Most of the teachers teach things in a different. You state and prove results in a very general setup, and reduce everything to special cases. But on the another way, you build your theory to a general setting, starting with the easiest case you know it. So the solvability one way X can be any space. We'll soon restrict to something. So solvability is Fx equal to y. When you say that for every y, there is a solution X, then you say that this is equivalent to something like a known to n. We are going more that. On the other hand, uniqueness, when you have unique solution, that unique solution, then is equivalent to 1 s. That's one way. So that's not what this is general setting. So when I write f from x to x, you may think that x is a very abstract space. Need not be. X may be where your physical solution lies, and you want to give, and y can be your data. So given data y, can you find a solution which is physical solution? For example, the many differential equations and other things or integral equations or many equations, you can put it in this abstract form and you want to know whether you can solve. So it's not that it's the thing. This is in a very explicit form. Explicit. You can have equations in the implicit form. So soon we will think it can be an equation from f of x, y equal to 0. F may be from some space x cross y to some x. You can change the spaces also. Okay. So as I said, when x, y, there are very interesting spaces. As I said, you may not be able to reach to that in my 4 to 5 lectures. So you want to solve. So this may be want to solve x in terms of y. That's again same thing. You want to solve x in terms of y. So one is in an implicit form and one is in an explicit form. So we will soon see some simple example where the solvability is an easy thing. There's also a concept of local solvability, and this is what I'm going to eventually work out. So the inverse simplicity function theorem are related to what is called the local solvability. We'll come to that. So let's start with an example, very simple example. That's what it will always help you to understand example. Let's look at this function f, whether you can solve all the time, whether you want to solve from R to R, and your f of x is equal to x square. And you want to solve uniquely. Fx equal to x square is equal to y. What is this? This is a very familiar equation. I don't want to think which you are very easy for you, but then so you have x square. You see, even such a simple equation, you see the trouble. So I'm looking for troubles where it will create. So you want to generalize eventually to Rn to Rn. So you look at it. If y less than 0, no solution. Y equal to 0, unique single solution. And y greater than 0, 2 solutions, you see. So you see, even such a simple equation like fx equal to x square, there are all the possibilities can happen. No solution, single solution, or multiple solutions. So that is what we happen. So look at here. So if I choose a point here, okay, this point, and if I choose a point here, so suppose this is a point A, and this is a B. So you have f of A is equal to A square equal to B. Okay. So given B, B is a solution, A is a solution. So I'm choosing B already on that. So on that, if I take any neighborhood here, look at a neighborhood here. And when I choose this neighborhood, I can choose any point in that neighborhood. You choose any point here. Okay, so I can choose this neighborhood. So I can choose some B minus delta. Delta may not be very arbitrary. You may have trouble, but I can choose some B plus delta. And I can choose any Y here. So you see, if I choose any Y here, okay. So corresponding to this point, you have these 2 points. And if I choose any Y here, I see I have a unique X. So what does that shows that? So there is a neighborhood of B. There exists neighborhoods of A and B. So this will be a neighborhood of A. I is called a neighborhood, and there is a neighborhood of B, such that when you restrict to that neighborhood, when you restrict your FR from this neighborhood I to this neighborhood J, then is 1, 1, 1, 2. That means you have that is unique solvability. So this is called a uniqueness feature, and this is possible when I am choosing when B is positive. Okay. Something is not working. This is not moving. Is some problem? Hello?
Is it that you have to open a new page or go to the next page or something?
No, I have already opened the page.
Oh.
The pages are there. Probably there is some, this is a drawboard. This may be a drawboard. So.
Or maybe you have to share it again. Is that?
I think maybe I have to stop sharing and then.
Yeah. Or the other thing is, if you share the whole screen, this might solve the problem.
It is showing 2 on 17 though, page number. It has moved to next page, it seems, right?
Yeah, it is showing 2 of 17.
Yeah, there are 17 pages.
Okay, yeah, maybe that's what you do. Stop share and share again.
Yeah.
I think it is still that page which on which you are writing.
Yeah, but it should. I don't know. There is a drawboard problem. I'll come back. What I'll do is that I disconnect. I will leave and
sure.
come back.
Yeah. Okay. Yeah. Sure. Yeah.
That's that. Something else is sharing. Can you hear?
Yes, sir. We can hear.
Yeah, I stopped sharing. Now you can try. Yeah.
Sorry for the trouble. Something stopped working.
No problem, sir.
Because these are all free software, so maybe they will have troubles.
Yes.
It's okay. Yeah, where are we put up? So, whenever you have b greater than 0, you have a solvable. So, what is written here? So, something written is gone at that stage. So, there exists for y in b, there is a unique x here. Unique x here. Okay. So in fact, what you are trying to say that there are neighborhoods. This is what I written. There are neighborhoods. I containing A, J containing B, such that F from I to J is 1, 1, or 2. And this in some sense, there is some problem here again. It's again not able to share it.
Sir, what is the problem? This,
I'm unable to understand. This is happening for the first time.
Oh, okay.
Because I regularly give lecture on this.
Is it? Are you not able to go to the next page? Is it?
Yeah. It was moving when I'm thinking, but first time it's happening, so I'm unable to find out.
There is this 4 squares, no, on the top where 2/17 is written. Something can we do over there?
No, nothing is working.
It's getting hung, is it?
Yeah, getting hung. That's a problem.
Oh, okay.
That's a problem.
I think writing pad is not connecting properly.
No, it's never happened. This regularly giving lectures.
Okay.
Regularly giving lectures on this.
No problem, sir. Sir, just to for like today's solution, I mean, in this Zoom itself have as a whiteboard. I mean, just for today, if you want to use it, that will also be okay, I guess. I mean, when you click on the share button, there will be something called whiteboard. If you click on that.
So shall I stop sharing this?
Yeah, you have to stop sharing and then now click on share screen again. There's something called whiteboard over there.
Whiteboard, yes.
Yeah.
Share that one.
Yeah, yes.
So it's the same thing same way continue.
Yeah, and to go to the next page, this at the bottom right there is a plus symbol. So if you click there, one more new page will open up.
This one.
Yeah, at the bottom right there is a square and a plus symbol.
Yeah, right.
Yeah. So if you click on that, then another page will open up.
Okay, fine. Okay. So the color we have to choose the same thing.
Yeah, I think in same way. Yeah. Do you see an option for color, or I forgot?
No,
I used
this I have not used, and there is an eraser, right?
Yeah, there is an eraser. There must be color also. There would be some floating panel where along that eraser only there must be some color also.
Yeah, which is eraser? I do not know. Maybe for this thing, because the eraser for us is yes, it should go. It's not going. Eraser. Anyway, sorry for this trouble.
No problem. No problem.
Yeah, it's happened first time. So that's why I'm unable to find the mistake. I never found the mistake. Anyway, so let me just go write something for today. Tomorrow we will see. So we are looking for fx equal to x square. And then we have seen that. So let me draw this picture once again. So if you take any A here, I have a B here with this B positive. And then you have seen that what I'm trying to say, that there are neighborhoods A and B, but for which this is a neighborhood I, there is a neighborhood J, and from I to J is unique solvability, local solvability. And this is what we are trying to solvability. But then the troubling point, what I want to look at it, if you look at this point, when I look at that point, F0 equal to 0. But then when B is here, no solution. When B is here, there are two solutions in this neighborhood. You will not be able to find solvability in the neighborhood of the thing. So looking for a trouble. So when you look at this f prime of x, that's equal to 2x. And then your f prime of 0 is equal to 0. So one observation is that here on the other hand, any other point, if you look at f prime of at any point is equal to 2a, this is not equal to 0 for a different from 0. So for all a different from 0, you can work out this way. But when a equal to 0, you have f prime of 0 equal to 0, and possibly that may be the reason. And we can see that indeed that's the reason. So let me give a simple result, which you can easily, I'm going to prove it. Result. Look at the function f from an interval AB to R, such that f is smooth, f is C1. Any of the notations are not familiar, please let me know. That means f is differentiable. C1 means set of all differentiable functions, differentiable, and f prime is continuous. F prime is continuous. Such functions are called continuously differentiable functions. Differentiable functions. Okay. So now assume, I'm going to prove a very simple, and all of you, maybe these are some of the earliest result, you would have seen it in your analysis. Assume f prime of a not equal to 0. Okay. So you have a function defined in some interval AB, and you have a function. Okay. And what I am trying to say that, also let me not complete take A. So let's take a point C, a prime of C. So I'm taking a point C. At this point, I'm telling that a prime of C is not equal to 0. What can you conclude? Can you conclude something from your experience? Any of you? Can anyone?
The function is either increasing or decreasing around that point.
That's how do you conclude that? That's what. See, mathematics, there may be some subtleties, and I want to give an argument. How do you prove that it's an increasing or decreasing?
If the derivative is positive, then
exactly. So you have that result. So I hope others are also following that. That's a result. You see, if f prime is positive, So that's why what kind of assumptions and if possible minimal assumptions you put it so that you will be able to prove it. So you see that is where these conditions are needed. You need the continuity of f prime. Just continuity of f is not enough. Differentiability is not enough. If f prime of c is positive, that implies there exists a neighborhood I containing c. So there is a neighborhood I. There is a neighborhood I. In such a way that f prime is positive, f prime of x is positive for all x in I. That's the argument you have to give. You see, that implies immediately, let me complete it here itself. F prime is positive, therefore f is strictly increasing. Strictly increasing. Once it is strictly increasing, you can immediately say, then you can compute few things. Let me not do that trivial thing. After that, you can find a j, I and j such that c contained in I and this j contained in f of c, such that f from I to j is 1, 1, 2. So you see, so you have implies local solvability. Local solvability. So the f prime, the vanishing of the f prime is the problem. So what we have precisely done is that, so if you have an interval, if you have any point which is 0, you are able to find an interval. So it will go, either it will be increasing or decreasing. If f prime of is negative, then it will be decreasing. So you can get an interval j and you can get an interval I, so that you have local solvability. And this is the result which we want to prove through inverse function theorem in a general case. Inverse. So what is the quantity you replace? What is the subtleties involved in that inverse function theorem? Yeah, so I will recall again. So what we are basically want to prove, we will state the result, because right now I will not be able to state. That's where you need to define the derivative of a function which are multivariable. Okay, so you will have an open set in Rn. And then to Rn. And if you have a point A in omega, B is equal to f of A. So this is essentially, I have not put the condition. I want to understand my local solvability. Of course, you need to introduce the concept of derivative. Then you need a bit of a linear algebra, which you are already given these years, these days. So you have a point here, A, and this map to a point B. So this is your Rn, and this is your Rn. And you need to have a neighborhood. So looking for a neighborhood, and you have an F here, mapping, and you want to have a neighborhood here, and you want to see this is your neighborhood U, this is your neighborhood V. So you are looking for F from U to V, 1, 1, 2, and you want to solve. So you, in that case, you can define 1, 1, 2. You can define G, F inverse, and you want to do it this smoothly, V to U, smooth way, your function. So the basic thing is that how do you replace this? So So how do we replace? How do we replace f is in C1 of AB? So you want to have the concept of derivative of f. Okay, so you want to replace what do you mean by C1? So the basically you want to understand that derivative of C1. And this is given by what is called the total derivative concept. We will do it slowly. Maybe derivative. Okay. Now I want to do what is the, so I want to motivate. So the what we are going to do through inverse function theorem. Now I want to do another example. You can have plenty of examples. So what I will suggest, try to do simple one-dimensional examples initially, and then you try to do few higher dimensional example. Here, want to motivate what is implicit function theorem for such a, again, whether the derivative is the vanishing of the derivative creates. So it's a two-dimensional function in an implicit form, x square plus y square minus 1. This is equal to 0. So the questions are what we want to ask. So you have only one equation, but you have two variables. Naturally, when you have one equation and two variables, you will not be able to solve. You can only represent one variable in terms of the another variable. So the questions are, can we solve? Can we get x in terms of y? So that's what you given question. Or can we get y in terms of x? Okay, but this, you know, this is a simple circle. So let's see where we can get it. So let's look at this one. Okay, this is your x square plus every point here. You know this because it's a familiar equation. So all the points on the unit circle are solutions to this equation. So if I choose a point here, this is your A, this is your B. Okay. You can always, you can see immediately find the neighborhood here. So given any y here, you can get an x here. So it is going here. So you can do this. So given any point here, y, you can get an x here. Okay, so you get an x here. So in other words, you can write if AB, if the point AB is here, you can immediately get neighborhoods in which you can get x is equal to g of y. I am not telling that how big is that neighborhood, but then, or you can also solve y in terms of x. Both ways you can get. You can take y here and then come back here, or you can take x here and get y here. So these intervals are known to in both ways you can do it. You can do it either solve x in terms of y, but only at this point. Now let's look at a troubling point here. Let's look at a point here. And this is the point 1, 0. Okay, let's see whether we can solve x in terms of y. Okay, so you understand that this is your y-axis. When I'm solving x in terms of y, so this is point A. So A is equal to 1 here, and your B is equal to 0. So if you choose a neighborhood here, you can find a neighborhood here. and you choose any point y here. So you can get a unique x. You can solve it. Okay. If you choose a y here, you can get a c. On the other hand, so let's look at my derivative now. What is my x directional derivative? You know already the axis derivative in the sense that partial derivative. So fx is 2x. Your derivative f of y is equal to 2y. So if I compute my f of x at 1, 0 is equal to 2. On the other hand, if I compute my f of y at 1, 0, it is 0. So you can solve x. So there exists a neighborhood of 0 for which x can be solved. For every x, you have a unique solution. That's a fact. But then, if I do here, now if I choose a neighborhood of x point that is 1, 0 here, you have no solution for here. So if a point chosen here, you have one solution here. If I choose a point here, you have a, okay, you have a point here. You have two solutions here. So if I choose a point x here, so you have no unique solvability here. There are two solutions here, and there are only one solution here. And this is the point where your derivative. So in this case, you can solve x in terms of y, but you cannot solve in terms of y in terms of x. So because your f of y at 1, 0 is 0. And this generalization of such results is leading to what is called the implicit function theorem. We will do the setting properly. So basically, f may be a mapping from some set E, open set. So you will have Rn cross Rn to Rn. You have to understand the significance of these sets. So let me go to this case. You have to understand this equation when you are having f from Rn to Rn. It is n equations in n unknowns. So you have to see the number of equations and number of unknowns. Okay. Okay, so here, this means you can always write your f is equal to f1, etc., fn. And you have two sets of variable, x, which is in Rn, and you have your y, which is in, so you're looking, this is in the implicit form. And here, so this is a vector in Rn, you have to understand, and this is a vector in Rn. So it's important to ask, so this is an n equations. So this is the n giving the number of equations in n plus m unknowns. So just like the earlier case, x square plus y square minus 1 equal to 0, you have one equation in two unknowns. So the question here you would be asking, so you have n equations, so can I represent given y? We will write more clearly. So you will have settings we'll give later. given y, can I write my x in terms of y? Can I solve x in terms of y such that f of in a smooth way g of y is equal to 0. Okay, and this is the result we want to these are two results we want to represent in the next 3 to 4 lectures, which so we will build the theory of total derivative, directional derivative, and all that. We will be doing that. Okay. Yeah. So what the ingredients which we need here is the total derivative, and then you need what is called the fixed point theorems. So we prove, we use one of the important Banach contraction theorem. Okay, and there are plenty of fixed point theorems, and fixed point theorems are extensively used to prove the existence of solution. There are various kinds of fixed point theorem. One of the fixed point theorem which we will present is the very, very common fixed point theorem, and the proof is quite easy for that fixed theorem, but the condition is little bit of stringent condition, and hence you may not be able to apply all the time. Okay, so we will come to that. So before we will do little more. So let me start by introduce. So all of you know what is a derivative in one dimension. So in higher dimension, we start with, I can define, as I said, the derivative of f from Rn to Rn, but we will do the derivative concept first for a scalar field, because there are many of the physical quantities or scalar field. Scalar field means f is from a subset omega from Rn, and it is a scalar. Okay. And what I will first do is what is called a directional derivative.
Sir, I think Rn to R.
Oh, sorry. Yes. I want to avoid any mistake, because I could not find the rubber here. Okay. Yeah, it is from Rn to R. And later, after that, we will do from f from omega Rn to R. Of course, as I said, the definition are similar. I want to motivate here the concept of gradient through concept of gradient later. And related other operations, like there are other important physical quantities, what is called a dive or divergence and curl. Maybe my colleague will introduce these concepts here. She will also be using the gradient. But then you can see that the gradient is a natural consequence coming from the scalar field. See, one thing before going to this why the thing, there are two things you have to see. When f is a derivative which is already defined from an interval, this you already know. I will anyway recall later tomorrow. When f is from R to R, then you already know what's a derivative. As I said, I will recall later. But if it is a multi-valued map, it's not the problem comes with a multi-variable, not a multi-valued. This distinction you want to make it. Multi-valued, if f is from AB to Rn, then f can be written as f1, etc., fn, and each fi is a mapping from AB to R. And immediately you can define the concept of derivative using the one-dimensional concept. So the one-dimensional, the way it is seen as a limit, cannot be immediately defined, use it for the definition of higher variable, multi-variable case. That's where the difficulty will come into play. So f prime of t can be immediately defined as f1 prime of t, etc., fn prime of t. Okay, you can do. So the multi-valued map is not a multi-valued map. With a single variable, is not a serious issue as far as the definition is concerned. Okay, not that every analysis for multi-valued map is trivial, but as far as the definition and immediate generalization, the issue is multi-variable. That's you have your x is equal to x1, etc., xn. And then how do we define? So the whole question is that how do we define f prime of a? And suppose you have a mapping f from, say, either omega subset of Rn to R, or more generally to Rn. How do you define f prime of a? The issue, question again, the question like that, is it enough to define enough the f in this case dxi? Okay, you will soon see that such kind of, you need a slightly finer definition. Just defining df by dxi. For a computational purpose, you may get everything to df by dxi, but then that may not be enough for a general thing. So anyway, so let me start with a directional derivative concept to begin with, and then we will continue tomorrow. I hope the lecture was a bit disturbed by not moving. That's okay. We will compensate it tomorrow. Okay. So, so you have a point. Okay. So you have a point here. So direction derivatives along a direction. Derivatives I can take a couple of minutes more.
Sure, sir.
Yes, sir, sure. Yeah. You have anyway 5 minutes according to schedule itself, sir.
Yes. Yeah, okay, it's up to 8:10.
8:10, yeah.
Okay. So what is a derivative? So I hope if you are not understood certain concepts, it's important to ask questions. You can also stop in between and ask me questions. Okay. So when I write suppose these points, a plus hy. That's why if you give lectures directly, you can keep on asking questions. So fix So fixing a point here, so fixed a point here, fix here, and also y. I don't know, most of you probably know it. I want to, sometimes the students are not comfortable these things. Everyone, so any point, a point A in Rn can be viewed. These are all familiar things you have studied, but I want to repeat this once again. Can be viewed in two ways. Viewed as a point, but the physicist quite often wants to view it as a direction, as a point. It can also be viewed as a direction. This is important for you to, for the physicist. Certain quantities, they would like to see it as a point. Certain quantities, they like to view it as a direction. For example, a position of a particle, suppose a particle is moving along in a space. And the position, they would like to view it as a position point, and the velocity, they would like to view it as a direction. So for any point A, you can view it as a point here, or you can view it as a direction. The advantage of point is fixed, but then when you have a direction, this you can keep it with the same direction. We say that it's both are same. You can take it to anywhere you like it. Okay, you can take this point any direction. So that's why when you are a particle is moving along a direction, when you say that you are a point is taken, this is a position of the particle, say xt, then the velocity they view it as, that's why they mark it. It is not this vector. This vector, when you keep it here, you get that vector. I'm sure all of you know this one, but I just repeated here. So this is what I'm trying to view this one. So you have a point A here, and then if I fix A, that is fixed as a point, that's fix a direction. When I say that, I fix a direction y. This is a point in Rn. Y is also a point in Rn, but we view it as a direction. So now consider A plus hy. So if y is this direction given, so if I mark here, these are my points of A plus hy. I'm interested when h is small. H is small. Positive and negative. So I want to find the variation of f. That's what the concept of derivative. So I'm going to give you the definition beginning with the limit. Later we will go to the other definition. So when I look at these points here, my a for h fixed, my a plus hy will be here when h is negative, or it will be here. So I'm defining my rate of change along that direction. Okay, so the rate of change. So that is what is called the derivative in the direction of y. Derivative in the direction of y. That is f of the standard definition, f of a plus hy minus f of a by h. You see, this is where your difficulties will come. So this variation is h is a scalar, small scalar. You cannot do it for in general, like one dimension. Why you cannot be denominator? So you look at this limit h tends to 0 of this one. And this is, we call it the derivative of a in the direction y. Okay. So if you take that direction y to be your canonical directions ei, you know that E1 is equal to 1, 0, etc. Then if you take your f prime of a in the direction ei, this is nothing but your, what you call it, your partial derivative in the direction I. Okay. So, so this is exactly your df by dxi in the direction a. You want to do it. So you can define the directions in all directions. You can do that. So let me begin. Tomorrow I will give you more examples. So let me give you a very simple example to begin with. And then we will do more examples tomorrow. F from Rn to Rn R with f of x equal to some dot product. B is fixed. B given fixed. Given fixed. This is given to you. So I want to compute at any point my f prime of a. Can anybody guess the answer without doing it? You have learned something earlier. Okay, I can write it, but anyway, let me do that exactly like the definition. F of a. Okay, f of a plus hy minus f of a by h. Right? And what is this? This one is nothing but b dot of a plus hy minus, what is f of a? B dot of a by h. That's a limit, right? Limit h tends to 0. And this is equal to b dot I cancelled, h cancel, and you get b dot of y. You see? That is your f prime of. This is same as f, right? This is same as. Do you feel this? Is this surprising or something obvious? Is this surprising to you or not? Anybody can answer me?
F is a linear transformation.
Yeah, so you are taking, that's what you are trying to eventually do it. So this is actually is linear, and this is and this is the motivations we are going to take it. Linear and linear, so that the derivative which we are going to do it is going to be the linear transformations. You are looking for the best linear approximation. So eventually tomorrow what we will be doing about the directional derivative or any derivative, the moment there is a derivative word comes into picture, you have to understand there is a linearity concept comes into picture. So you are looking basically the derivative, in some sense you are looking for a good approximations. When you have the function is not linear, it is curved, it creates trouble. So you are looking for best linear approximations to your function. And your given function is itself is linear, your derivative has to be the linear function itself. So this is no longer is a surprising thing, and that's it. So there is. So one more thing I will do it, and because I missed a few minutes, and then I will do that one, the last one. So we will anyway elaborate more on again and again. So what is this? I'm putting the same direction derivative in the direction y. I don't call it a directional derivative. Directional derivative has to be unit vector. I'll come to that tomorrow. But what I have introduced is the derivative in the direction of y. So you have to distinguish between the directional derivative, and because there is a normalization parameter to be used when it is a directional derivative. So you can define a function.
One problem.
Yeah.
Sorry, last problem you said b dot x, right? I mean, but it is a function from Rn to R. So
yes,
what else?
It's a dot product.
Oh, dot product.
Yeah. It's a dot product. Okay, this is equal to b1 x1 plus etc. b2 x bn xn. Is that okay?
Yes.
Okay, it's a dot product, and this formula there is no issue. These computations are because the dot product you can take it inside. There is no problem. So and h is a scalar, and the b dot of hy is equal to h into b dot of y. So that h cancels. H comes out because h is a scalar. So the computations is done works for the this thing. Okay, thank you. Yeah, so define, I'm putting the same thing in a little more convenient way. Each time you don't have to write your thing. You define gh, a and y are fixed. So you can define f of a plus hy. So I can compute if f is smooth. Okay, I have not defined yet the smoothness because I have not defined the derivative yet. But still, assuming that f is differentiable if that limit exists. So I'm doing what is one-dimensional thing. So I have not so far imposed any conditions of f, even in the previous case. Assuming that limit exists, limit may or may not exist. Okay, so you can compute g prime of h. Okay, if you compute g prime of h, you have to be g prime at the point h I am computing. So you have to use a different parameter now. Limit t tends to 0. This is a plus hy plus ty minus f of a plus hy by t. Okay, that's the way. This is nothing but f prime hy evaluated in the direction of y. Okay, and then if you compute your g prime of 0, that is nothing but your f prime. So I can have a, I'm putting it in a slightly different way. So this is exactly, so when I computing this one, so you have a point here, and I'm defining a one-dimensional function along this line. This is a plus hy direction. I'm defining a one-dimensional function, and I'm computing g prime at any point. So I have defined the function g along this line, and then I'm computing g prime of h at any point here. And if I compute that the g prime of 0, I get here. That's what I said. You have a one last example. Maybe I will to do this. One more example. I can define f from Rn to, this is something like a, earlier is linear. Now I give you another example, which is, I'm taking very, very simple example. To understand the theory, you don't have to take a very complicated example. Start with very obvious examples which you are familiar with it. Fx equal to norm of x square. Okay. So I want to compute your, so what is your gh here? I will not do all the computation. F of a plus hy. This is quadratic. This is not linear. There is a difference between b dot of x and norm x square. So this you have to write it as the dot product a of hy dot product a of hy. So you can easily compute. So what do you expect? So you want to compute your g prime with respect to h, which you can compute easily, and then put h equal to 0. Right? You can easily compute a dot, you can expand it. And so you see there is an easy way of doing. Once you have this representation, you can immediately compute g prime of h and then substitute h equal to 0. So what do you expect? The answer. Anybody can tell me immediately? Now, those who are, you don't have to, whenever we have a norm, you just, I told you, you try to think it always in the easier case. What is the easier case? The easier case is when n equal to 1. This is nothing but x square. So, and then you know that your f prime has to be 2x, and you have to see it as a linear map. So, and at the point here, okay. So, you want to compute your f, this is at 2 a dot of y. That's what you can just do this computation. It has to be linear. So, a y. You see. So I'll stop here. You just do this computation. One more line. You can do that one. And what I'm saying that you don't have to worry about this one. So when it is x square, its derivative in your usual sense is 2x. And you want to compute at a. So it's 2a. And then you view it as a linear map. So it has to be 2ay. And these things we will elaborate tomorrow. So today, if you have any questions immediately, please feel free to ask questions. Okay. So you don't have to worry about asking questions anytime. Any questions you want to ask?
So direction derivative in vector calculus is having the same meaning or?
A vector calculus, you mean when it is a vector field?
Yeah, but in that case, we will have the one surface and we will find out the normal, and along any vector we calculate. That means that is nothing but
you will have essentially the same meaning, but then the definitions has to be carefully given. Suppose you are moving along a direction. When I define a direction, you can also always define a derivative along the tangential direction. So at each point, you can define derivatives along a tangential direction. And then you can do that. End of it, the meaning will be the same. But if you are moving a curve along a surface, then you have to have these things should be defined appropriately in the concept of manifold and other things. Okay.
In a layman, in vector, can we say that is a factor of the normal in the direction of the vector, like that, because we are taking the dot product of the normal in that direction of the any vector?
You will be able to interpret. Yes, you will be able to interpret. You have to any derivative, you will be able to interpret appropriately. No doubt. So maybe I may not have understood your question thing, but yes, any derivative has to be in some sense this way to define.
Here in the real also the same we can interpret.
Hello.
Yes, sir. Can we say here also in the real analysis also instead of vector? Something.
What is the question? Precise question.
As we say in the vector calculus, that is the that is a factor of the normal in the direction of vector. Can we say the similar thing in a real analysis? Means in a layman, something like that?
That's what I have not understood your question properly. Maybe you can frame it little more, maybe discuss tomorrow.
Okay, sir. Okay.
If you frame it properly. But what I want to say is that whatever derivative or direction, any derivative you are looking in anywhere, it will be. I don't know whether you are asking a question regarding the derivative or something else. That's my doubt. Okay. So
Okay,
if you
sir.
can frame it to your problem precisely, little more. Yes, in a layman point of, so what I have discussed so far are more or less a layman point of view combined with the thing. Maybe I will stop sharing and then I can see you also. Okay, come. Yes. Okay, so we will answer that for sure.
Sure.
Anything else? Yeah.
Are there any other questions? Okay, if not, then let me thank
so
Professor
please give me a proper input, then accordingly I can modify my. Sorry for the whole some trouble today's thing. It's a little disturbed.
No problem, sir. I think we would have got very nervous in this kind of situation. I was wondering how you were managing without an eraser for 1 full hour. That was really wonderful to see.
Nervousness won't come because we are lecturing for so many people.
Yeah, I mean, no, this kind of technical difficulty happens. I mean, usually some of us get very, nervous.
No. You don't get. I don't get nervous. I get that flow, and it will disturb the participants. That's only.
Yes. Yeah. No, it was
not about what I want to talk. That nervousness won't come.
No, but I think it was fine actually. It was.
Yeah, it was really nice.
It didn't interrupt much. So, by the way, tomorrow you remember 6 o'clock you will come, right?
Yeah, I will come at 6 o'clock.
Okay. Oh, okay.
Also, just a suggestion. I mean, if you also want, we could have 1 hour lecture and 1 hour tutorial if the tutors are also ready, or we could have just 2 hours of lecture.
I will cover something. I will try to introduce all this. Maybe I'll try to reach the inverse function theorem in a proper.
Okay, so then Saturday
only time there.
Sure. So only Saturday only we will have the tutorial.
Yeah, Saturday they can have the tutorial.
Okay. So,
by the way, this thing that you were writing on, Nandakumaran, I mean, is that already shared with you, Sushoma? The thing that you were writing on, the notes, I mean, is that a file that can be shared or something?
No, I can share it, but now with this new one, I don't know how it does.
So actually, there is
one I can always share.
In this also, there might be a save option in that whiteboard. I
don't know. The other thing happened for the first time, so hence I have this issue.
Sir, do you see this on the top? There is another, floating panel, right, where you have this select text, draw, stamp, eraser, and then there is a format. Is it visible to you when you share the whiteboard? Actually, if you have closed it now, I think you will not be able to save it.
Yeah, I have already closed it.
Yeah, so it's okay. Yeah, so it's okay. No problem.
Okay, no problem.
Yeah.
Now, other things I can always, what I was writing, I can always share because I know that one. And that happened for the first time, I don't know. So I couldn't solve it.
No problem.
Because I use that drawboard. I don't know drawboard why it came like that 2 times.
No, it was anyway really nice. I mean, it did not really affect the flow.
No, whatever I wrote, it's today missed it, right? Did you record it or something? No.
Yeah, we are recording it. Yes.
So through that you will get everything.
Yes. Recording is anyway there. Yeah, recording is there. No problem. Yes.
Yeah.
Okay, then we will start. We'll do tomorrow.
Okay.
Yes, sir. Yeah.
Right.
Thank you. Yeah. Good night, everyone.
Yeah. Inputs will always help, so we can modify our lectures accordingly.
Sure, sir. I'll send your email ID, and if any participants wants to give some feedback, then they can write it to you or even to me. Anything is fine. Or Manjunath.
Okay.
Okay. So, yeah. Okay. Yeah. Thank you so much, sir. Yeah.
Thank you. Bye.